So I'm going to start live streaming now. Just a second, I'm going to have to.
It's getting brighter outside.
Oh, what time is it for you?
6 a.m. in the early morning.
Oh, thanks for joining us.
Yeah.
Hi, Karen. How are you?
Good, thank you. Hi, Ren.
Hi.
Karen. Excellent. Okay. And then I'm going to share the screen and then. Okay. Oh, sorry. I have that. Oh, sorry. Oh, no. Okay. So it's going to be okay. Maybe we can share now. Okay, you guys can see that. Okay, perfect. Great. So let me start. Things I think hopefully people will come in a minute. Obviously, a few more people in there. So thanks once again for joining us on the online SPICE and SPIN+X seminar series organized here by myself and the SPICE Spin Fundamental Disciplinary Center SPICE with the help for Angela Wittmann and Karen Eversosite, and in collaboration with the SPIN+X Collaborative Research Center led by Martina Schiemand and Burkhard Hillebrands in Kaiserslautern and Matthias Kluwe in Mainz. As you know, we have the seminars at 3 p.m. On German time, and just unfortunately that today is a speaker. So you have still, please check out the seminars for next week's. But today's speaker is Cheng. He was it's actually it's wrong. Not postdoc, it's a professor at the University of California. Something's wrong in that CV, and then he's actually an expert on exotic transporting phenomena, in particular spin and magnetic systems in our field. As in UC reside, and unfortunately has to get up at 6 in the morning to give us this this lecture. So with that, I'll take no more time, and then please, Rang, if you don't mind, share your screen.
Sure.
And we'll ask the rest of us, we will mute to give you guys more bandwidth, and go ahead and
so
start. And everybody, please ask ask your questions in the Q&A, or afterwards I will give you the floor to answer. Okay.
Okay. Can you see my screen? Yeah, thanks very much. Thanks very much for the very warm introduction, and thanks for inviting me to present our latest findings on this very prestigious SPICE seminar. So today I'm going to talk about our latest findings, and the title is Driving Exchange Mode Resonance as Adiabatic quantum motor with 100% mechanical efficiency. So this work was primarily done by my PhD student, Junyu Tang, and the project was part of a large Muri grant, a Muri project in the United States. And this work has been submitted recently, and here's the archive preprint, where you can check for more details. Okay. So, okay. So here's the talk. Let me, on the slide. Okay. So we're going to talk about the, the voltage-induced work in my presentation today. But to motivate why we gonna study voltage-induced torque, let me first briefly comment on the problems with current-induced torques. So we know that the current-induced spin torques have been an active area of study because they are fundamental to the electrical manipulation of magnetic materials, which holds potential in realizing low dissipation magnetic memory. So in the last 2 decades, the study of spin torques has gradually migrated from the traditional spin valve structure to the spin Hall effect-based devices, where the spin flows perpendicularly to the driving charge current. However, although spin generation becomes much more efficient by using the spin Hall effect, the mechanical efficiency is still very low. And this is because, the transition from spin valve to spin Hall does not change the fact that the spin torques are still current-induced torques, such that the Joule heating is very significant. And the Joule heating is a universal problem with all current-driven systems. So here, a very rough estimate about the mechanical efficiency can be done this way. So here, this is the energy consumption rate by the magnetization dynamics driven by the current-induced torques. And here, this is the total input electrical power, where the JC is fixed by external circuits, while the effective conductivity includes the intrinsic conductivity as well as the spin Hall magnetoresistant, the conductivity of spin Hall magnetoresistivity. So a rough estimate of the mechanical efficiency in the spin Hall geometry, gives us only a number on the order of a few percent. So the mechanical efficiency is actually very low, even though we know that the spin generation efficiency is much higher than the traditional spin valve. So how can we gonna fundamentally solve this big problem? How can we, solve the Joule heating problem? So, the Joule heating is actually not the only problem associated with the spin Hall geometry. So on top of the Joule heating, we still have other limiting factors that further reduces the actual efficiency of the functioning of the device. For example, the spin Hall angle in typical heavy metals is very limited, which only converts, a small fraction of the driving current density into the spin current density that drives the magnetization. And we know that the generated spin current is subject to spin diffusion and spin backflow, which combined, renormalizes the effective spin mixing conductance on the interface that characterizes the actual spin absorption rate by the magnetization. So combining the Joule heating, which is the largest problem with this geometry, and the small spin Hall angle, spin diffusion, spin backflow, everything combined, then eventually we have a very limited mechanical efficiency. So in order to, solve this problem, we should avoid the participation of Joule heating resulting from the dissipative current. But this sounds to be, basically impossible. And to look into the problem, let us check the 3 fundamental types of currents in physics. So we know that there are 3 physical currents. One is the dissipative current, and the other is the superconducting currents, and the last type is the adiabatic current. So for the dissipative currents, we basically refer to the Ohm's law. So we all know this. So if we apply an electric field to a conductor, then you drive the electrons to move. But then the electron will collide with the phonons, with the lattice background. So it converts the kinetic energy acquired from the electric field to waste heat. And this is where Joule heating is generated. So this is for the dissipative currents, just the Ohm's law. And for the superconducting currents, the physical picture is entirely different. So below a critical temperature, when the system enters into the superconducting phase, then electrons can pair up. So this is known as the Cooper pair. The electrons can pair up by exchanging the phonons or lattice vibrations. After that, the Cooper pairs can move cooperatively, so that the electrons can move basically without any resistance. So this is why it is known as superconducting currents. So in a superconducting current, it's a persistent current where the resistivity is 0, while the conductivity goes to infinity in the most ideal case. But the problem with the superconducting current is that it only exists at a very low temperature. And even today, the highest known superconducting temperature is still below that of the liquid nitrogen. I mean, at the standard in the standard pressure. So this limits the capacity of utilizing the superconducting currents in our electronic devices. So then we should resort to the third type of physical currents known as the adiabatic currents. So what is an adiabatic current? The idea was originally proposed by the late physicist David Thouless. So in an adiabatic current, the current is actually pumped by the adiabatic time variation of a geometrical parameter known as the adiabatic parameter. So it is the time variation of the adiabatic parameter that generates the currents or the physical motion of electrons or other particles. So this is known as the Thouless pumping, and sometimes also known as the topological charge pumping, or simply adiabatic pumping. So, and by the way, so David Thouless was awarded the Nobel Prize in Physics in 2016, partially because of this proposal. So here, this is illustration, a schematic illustration of Thouless pumping. And so this machine is known as the Archimedes machine, where a rotating screw, pumps the particles from one end to the other side of the device. And in fact, the Archimedes screw has been utilized, in pumping waters from river in the early development of agriculture science. So what the Thouless actually did is to apply the idea of the Archimedes screw to the nanoscale, to the nano world, where the quantum mechanics governs the transport. And there's no water flow in the nanometer scale, but what plays the role of the water flow is the electron flow or the electron current. So this is known as the Thouless pumping, where the current is purely adiabatic. This is fundamentally different from the superconducting current and the dissipative Ohm's current. So a compelling feature of Thouless pumping is that after one cycle of the adiabatic parameter rotation, the amount of charge pumped from one end to the other end is exactly quantized. And this quantization is attributed to the topology of the system. So we know that in nature, there are two things that are super reliable. One is quantum, and the other is topology. So the Thouless pumping integrated the two reliable things. So the idea integrated topology with quantum. So sort of you get a super reliability. So in real system, what actually plays the role of the rotating adiabatic parameter can be any physical quantities. But in our case, we're going to consider the magnetization that plays the role of the adiabatic parameter. So the only requirement in our case is that the typical frequency of the magnetization dynamics is much lower than the band gap. so that the adiabatic condition is satisfied. Okay, so now we know that this is the thoughtless pumping. And then, so in 2013, there was a very interesting idea that proposes to operate the thoughtless pump reversely. So the proposal was the reverse effect of a thoughtless pumping. So here we're going to consider an insulating system where the adiabatic parameter just functions as the gears that are coupled exactly to electrons. So once we apply a voltage through this insulating system, then as the reverse effect of a thoughtless pumping, the applied voltage or electric field can actually act on the magnetization or the adiabatic parameter through a voltage-induced torque. Because there is no transport current, this is the insulating system. And then the dynamics of the magnetization through thoughtless pumping will generate an output current. So here, from the electric field to current, the only channel is to drive the adiabatic motion of the magnetization, while the ordinary Ohm's channel is completely closed because we are considering an insulator. So by doing so, we can potentially achieve a 100%, an ideal 100% mechanical efficiency, because all the input electric power will first convert it into the magnetization dynamics, which we regard as the useful work. And then it is the magnetization dynamics that pumps current. So from electric field to current, all the input power will be eventually converted into the magnetization dynamics. That is how we could get a 100% mechanical efficiency. But the condition is that the system must be perfectly insulating. If there's a leakage current, then the leakage current will produce a little bit amount of Joule heating. But practically, this is still of an extremely high mechanical efficiency. Okay, so but to realize such a machine, which the author termed as adiabatic quantum motor, so the entire adiabatic quantum motor relies on the combined effect of the voltage-induced torque and the thoughtless pumping effect. The two effects reciprocally, the two reciprocal effects can function simultaneously. Okay, so that is how an adiabatic quantum motor can function. So now here's the thing. In order to build such an adiabatic quantum motor, we first need to find the voltage-induced torque as the reciprocal effect of thoughtless pumping. Okay, so in order to see if this is indeed possible in an insulating system, we adopt the following formalism. So we're gonna use a semi-classical formalism developed by my PhD advisor, Professor Cheng, and an early PhD student in our group, Sundaram, who is now a physics professor in India. So the Sundaram new formalism, generalizes the idea of thoughtless pumping to a more general context, but also comes with a more intuitive picture by describing the Bloch electrons as semi-classical wave packets. A semi-classical electron wave packets consist of two parameters, the center of mass position and the center of mass momentum. So the physical motion of such a Bloch electron wave packet is described by the orbits in both the real space and the momentum space. So in the Sundaram new formalism, the central quantity, that it determines multiple transport effect is known as the Barry curvature. And what I'm showing here is the Barry curvature tensor that Okay, so the Berry curvature can be understood as a generalized gauge field residing on a grand phase space. Depending on the system, the physical conditions of the system, the Berry curvature can have, multiple parameters. And here, in the most general scenario, the Berry curvature is the gauge field living on the grand phase space that connecting the momentum, time, and space. Okay, so an apparent advantage of this formalism is that a wide variety of physical phenomena, physically transported phenomena that are seemingly unrelated can actually be understood in a unified way under this formalism. So different physical phenomena just turns out to be, different manifestations or different components of the Berry curvature tensor. For example, the KK component, the Berry curvature living in the momentum space, can well explain the anomalous quantum Hall effect. Well, the real space Berry curvature can explain what is known as the topological Hall effect. So the real space Berry curvature mimics a real magnetic field because of the spatial variation of the magnetic spin texture, which curves the motion of the electron. So this is known as the topological Hall effect, in which the electron, interacts with the skyrmion and, develops a transverse motion. So the physics behind this topological Hall effect is actually the real space Berry curvature. And the location time cross components in the Berry curvature tensor is what behinds the spin motive force, So the spin motive force actually refers to the generation of a voltage across a nanowire in the presence of a domain wall. So if you can move the domain wall, for example, by applying a magnetic field, then the motion of the domain wall can generate a small voltage across the wire. So the whole nanowire can function as a battery due to the motion of the domain wall. And this is known as the spin motive force. And the spin motive force is nothing but the integration of these two Berry curvature components. So those are just a few examples demonstrating, how powerful this formalism can give us. But in fact, in our considered system, we only consider, spatially uniform magnetization. So all the spatial derivatives actually vanish. So in our specific case, the last row and the last column in the Berry curvature tensor vanish identically. And also the time dependence in our system is attributed to the magnetization dynamics. So in our specific scenario, the Berry curvature tensor reduces to this, where the parameters are the center of mass momentum and the magnetization orientation only, while all the other components simply vanish. Okay, this is our starting point, and because the T dependence is attributed to the magnetization dynamics, which plays the role of the adiabatic parameter. Therefore, the effective dynamics of our system is described by the coupled equations of Sander-Neel equation and the Landau-Lifshitz-Gilbert equation. So in this coupled equation, the electron motion is described by the first two equations, and the magnetization dynamics is described by the last equation. Well, the Berry curvature here couples the electron transport and the magnetization dynamics through the off-diagonal Berry curvature. So here the MK components refers to the Thouless pumping that we just introduced. Well, its reciprocal components, the omega Km, that is what we are seeking for, the voltage-induced torque. And specifically, if we insert the K dot into the third equation, into the LLG, then we are creating a term that is proportional to the applied electric field that can directly drive the magnetization dynamics. So by combining the first equation and the third equation, then we have a theoretical toolbox to calculate the voltage-induced torque. So here we also have a term that arises from the MM components in the Barry curvature tensor. And that physically represents the renormalization of the Gilbert damping because of the topological electrons. Okay. And reversely, for the topological charge pumping, so long as the Fermi surface, so long as the Fermi level lies in the gap of our system, and the frequency of the magnetization dynamic is much smaller than the gap, then the electron dynamics, as this just mentioned, will be solely coming from the adiabatic thoughtless pumping. So the current in our system is purely adiabatic, which does not produce any Joule heating. So this is our formalism, which serves as the theoretical basis for the following calculations. So we have a coupled magnetization dynamics and electron transport, and everything is nicely represented by different components of a Barry curvature tensor. Okay, so basing on this formalism, we first apply the voltage-induced torque term to a bilayer heater structure consisting of a topological insulator and a magnetization and a ferromagnet. So here, by calculating this voltage-induced torque, we find that its spin orbit torque is actually a field-like torque if the Fermi surface lies in the surface gap. It is a field-like torque, and the effective field is proportional to and parallel to the applied voltage or the electric field. And if you flip the Z component of the magnetization, then the effective field also flips sign. So there are a lot of work studying such a structure, but this formalism can capture the two effects in a really nice way from a really rather intuitive physical picture. And also we notice that there are disputes among the literatures that whether the spin orbit torque in such a system arises from the edge states, because this is a gap system by the proximity effect, whether the spin orbit torque arises from the edge states or the bulk states. So some literatures, for example, this paper believes that the spin orbit torque here arises from the edge state. But according to our calculation, we find that actually the spin orbit torque arises from the bulk state. So this is not simply an edge state effect. Well, one may argue that there's a bulk edge correspondence, so everything should be consistent. But the edge bulk correspondence is actually applies to the omega kk components, which gives rise to the Chern number. But here, the relevant component is the km component. So literally speaking, the bulk edge correspondence is not a very sufficient argument to this scenario. Okay, so this is just how things turns out in a topological insulator and a magnetization ferromagnet heater structure. But this is not what we are going to solve in this work. Our focus is a trilayer structure. So we're going to consider a trilayer heater structure consisting of two ferromagnets center reaching a topological insulator in the middle. And once again, without a doping, without gating, the Fermi level lies in the gap. So this is the gapped system. And this is the effective Hamiltonian for the surface electrons, where we see that there's additional term that has no counterparts in its bilayer, in the bilayer case. And this A term represents the mixings between the top and the bottom topological surface. And here, by using our formalism, we find that the effective field induced by the applied voltage acting on the top and the bottom layer are actually of opposite sign. So the voltage-induced torque acts oppositely on the top and the bottom ferromagnets. And what does that indicate? That indicates that if we prepare the system as an autoplane, parallel configuration, then under the voltage-induced torque, then the two ferromagnet will be evolving towards opposite directions. So eventually, the voltage-induced torque will excite what is known as the exchange mode, in which the two ferromagnets precise in the same way, but with a pi phase difference. And once again, we have a surface gap, but we have edge states, in the one-dimensional edge states. But this edge state, according to our calculation, does not directly drive the magnetization, even though the edge states is essential for the quantum anomalous Hall conductivity. So here's our finding. And, by claiming that the voltage-induced torque can excite the resonance of the exchange mode, the frequency has to match. And here, the eigenfrequency of the exchange mode can be much higher than that of the ferromagnetic mode, of the FMR frequency. So depending on the strength of the interlayer exchange coupling, the actual eigenfrequency of the exchange mode can be as high as 100 gigahertz, basing on the predictions of two recent papers. So these papers predicted that the effective exchange coupling in such a structure can be as strong as the exchange interlayer coupling in the traditional spin valve. So that is how we get a much higher eigenfrequency by exciting the exchange mode. So, okay. Now we performed a very detailed numerical calculation of each component of the effective field associated with the voltage-induced spin orbit torque as functions of the spherical angles of the top magnetic layer. And we did this for both the FMR and the exchange mode resonance, which we term the EMR. So we did it for both FMR and EMR configurations. So here we find that for the FMR mode, or the uniform precession mode, for the FMR mode, the X component, which is parallel to the applied voltage, is the dominant component. But different from the bilayer case, in which we only have the X components. In the trilayer case, we also have a small Y component and a Z component, even though they are much smaller than the X component. And this is because we also considered a finite mixing of the top and the bottom topological surfaces. So here for the X component, the dominant components, if we flip the direction of the Z of MZ, then it changes sign. So on the equator, the gap closes, so the adiabatic condition is violated on the equator. So that's why we just remove the equator from our phase diagram. Then for the exchange configuration, which we gonna discuss in the following, then there are three distinct topological phases as we vary the polar angle of the magnetization. So here, besides the topological non-trivial phases, we also have a topological trivial phase in the vicinity of the equator. And the phase boundaries takes place at around 55 and 125 degrees. So here, what is interesting is that the spin orbit torque exists for the topological non-trivial phases. Well, that is easy to understand, but the spin orbit torque is non-zero even when the band topology is trivial. Okay, even though we have a much smaller spin orbit torque, but is not zero. Okay, so before discussing how the Trilayer system as a whole can function as an adiabatic quantum motor as we conceived, let us first look into the resonance behavior of the system, which is one side of the story. Okay, so for the exchange mode resonance, we can either sweep field or sweep frequency, but here for simplicity, let us just consider a frequency sweep. So by solving the linearized Landau-Lifshitz-Gilbert equation, then we find that the top and the bottom magnetization, here the MT and MB, are indeed rotates with a pi phase difference, which is represented by the plus or minus. And the two, the top and the bottom magnetization, they rotate with a pi phase difference, but they have exactly the same amplitude. So they share the same longitudinal and transverse dynamical susceptibility. And the real and the imaginary part of these two dynamical susceptibility components are plotted here. So this is for the susceptibility. And by the way, here we just use a very reasonable exchange resonance frequency as 50 gigahertz. Because as I mentioned, the interlayer coupling can be extremely strong. So a 50 gigahertz, a 50 gigahertz resonance mode, that is a very reasonable estimate. So what is the plot in the bottom? That is for the polarization of the exchange mode. So we see that right on the resonance point, the polarization is perfectly circularly polarized. I mean, this is a perfect circularly polarization. But when we go off resonance, then on the high frequency side and the low frequency side, then the polarization of the exchange mode gradually evolves towards two perpendicular linear polarization. So, okay, so this is only one side of the story for the resonance only, or this voltage-induced torque driven exchange resonance. Now, for the system to function as an adiabatic quantum motor, we must consider the voltage-induced torque and its reciprocal effects, or the thallus pumping, simultaneously. And in this regard, we're going to insert the Landau-Lifshitz equation into the topological charge pumping in order to eliminate the magnetization variable. And by doing so, we actually establish a linear relation between the driving voltage and the response current by eliminating the the magnetization. So this relation tells us that the system have an effective admittance, or the AC conductivity, whatever you call it. So the combined effect of the voltage-induced torque and the thallus pumping eventually manifest as an effective admittance of the system. And this characterizes the electrical response of our proposed adiabatic quantum motor. So the physical behavior of the quantum motor is all, is all characterized by this effective admittance. So this is our numerical results of this effective admittance for the longitudinal components, sigma xx, and also for the transverse component, the sigma xy. So here, for both the transverse and the longitudinal components, we see that the effective admittance experiences a sharp peak, a very sharp peak around the resonance point. This is the exchange resonance. And that is because, when we go off resonance, the system does not, the system is a purely insulator, and there's no magnetization dynamics, so there's no current at all. That is why the effective admittance goes to 0 when we go off resonance. But for the transverse admittance, it is, numerically, it is much smaller than the intrinsic quantum anomalous Hall conductivity, even at the peak value. So that means in the transverse direction, it is very hard to measure this prediction. But in the longitudinal direction, this is an insulator, so the intrinsic conductivity goes to 0. Therefore, the frequency dependence of the effective admittance becomes a very significant effect, and it's very easy to detect. So basing on the peak behavior, the peak pattern of the longitudinal admittance of the proposed adiabatic quantum motor, then we consider the following circuits. This is a simple circuit to detect our prediction. So here the trilayer effect is connected in series with a reference impedance. And we measure the voltage drop across this reference Z0. So here's what we expect. When the system is off resonance, then the impedance of our trilayer is infinity because the admittance goes to 0. Therefore, there's no current flow. So the voltage measured here is 0. And when the system is on resonance, then the admittance experiences a sharp peak. So the impedance experiences, the impedance reaches the minimum. And when the impedance reaches minimum, then by dividing the voltage, then we expect that, the voltage meter reaches its maximum on resonance. So this is how we measure the device, how we measure the exchange mode resonance. So to better understand the electrical response of this trilayer device, we would like to find an effective circuit to characterize its electrical response. So to this end, we're going to use the impedance instead of the admittance. Then, the system impedance turns out to be this, where the omega is the driving frequency and omega r is the resonance frequency and alpha is the Gilbert damping. So the system impedance can be decomposed into two terms, where the first term can actually be represented by a resistor in series with a capacitor, while the second term can actually be translated into another resistor in parallel with an inductor. So this is the effective circuit that exhibits exactly the same electrical response as our trilayer. So by equating the system impedance with the impedance of this effective circuit, then we can exactly solve all those parameters in the effective circuits. Okay, now we are ready to make our central claim, the mechanical efficiency. So now with the effective circuits, it's actually very easy to compute the energy consumption by the magnetization dynamics and the overall and the total electrical power injected into the system. So, after all the manipulations, then we find that each of the terms just cancel one by one. And ultimately, we get a 100% mechanical efficiency, which indeed affirms our conceived picture of adiabatic quantum motor. All the input electric power is 100% converted into the magnetization dynamics in compensating the Gilbert damping, let's say. So, and this is quite a universal conclusion, because even though even when we manipulate the system size, and the system parameters, we simply does not change this conclusion. So this is a pretty robust conclusion. But in real materials, we always have imperfections, especially that the topological insulator may not be fully insulating. We know that a topological insulator conducts a little bit of current. If that is the case, then we should consider the imperfections arising from the leakage current. And for the leakage effect, the effective circuits for the leakage effect is a leakage capacitance in parallel, in parallel to a leakage resistance, which indeed gives rise to a Joule heating, okay? But using the typical materials parameters, we estimate that a practical mechanical efficiency in the presence of the leakage effect can still be about 50%, even for imperfect topological insulator, which does conducts a little bit of current. However, we can reduce the leakage-induced Joule heating by proper device engineering. For example, we can reduce this by using thinner ferromagnetic thin films and manipulate the aspect ratio of the device. And there are a lot of ways to engineering the device in order to reduce the leakage effect. And also, with the improving materials qualities of the topological insulator, we expect that in the future, the actual mechanical efficiency can indeed be pushed to its theoretical limit. So as a comparison, the mechanical efficiency in the traditional spin Hall-based magnetic resonance is only on the order of 1%. And once again, this is because of three things: the Joule heating being the dominant factor, and the spin diffusion and the spin backflow, which reduces the effective spin mixing conductance, and also the spin Hall angle is very limited. So that is how we get such a low mechanical efficiency. So even with imperfections, our proposed device can still function way more efficiently than the spin Hall-based magnetic resonance. So the last thing that I would like to comment on our device is the Ørsted field. We know that in current-driven systems, we have Ørsted field, always accompanying with the current-induced torques. So according to Maxwell equation, a flowing dissipative currents will generate a stray field to the outside. So eventually, what actually drives the magnetization dynamics is the combined effect of the Ørsted field and the spin transfer torque. And in typical devices with a current-driven spin torque, it turns out that the Ørsted field and the spin torque field are comparable. At least they are on the same order of magnitude. But in our voltage-driven system, we do not have any transport current. The only current we have is the so-called displacement current. And the displacement current can also generate a stray field. But now the stray field is frequency dependent. It is frequency dependent. And here, what plays the role of the spin torque is not the current-induced torque, but the voltage-induced torque, which can be attributed to the vibrational motion of the bound charge. So here, this is the diffusion current that gives rise to the spin transfer torque. And in our proposal, it is the vibrational motion of the bound charge that generates the voltage-induced torque. So in our proposed device, we also estimate that even at such a high resonance frequency, the relative strength of the Ørsted field is orders of magnitude smaller than the voltage-induced spin orbit torque. So in our device, if this is pushed into a real experiment, we can simply ignore the Ørsted field generation. So only the spin torque dominates. And that concludes my talk today. So we propose that a ferromagnet topological insulator and a ferromagnet Trilayer heater structure can be operated as an adiabatic quantum motor to achieve a much higher mechanical efficiency. And it is the voltage-induced torque that underlies this proposed mechanism. So we also find effective circuits to characterize the effective electrical response of our Trilayer. And we estimated that the Ørsted field is always negligible in our device. So one of the ongoing investigations is the generalization of this idea to intrinsic magnetic topological insulators without heater structure, which we expect, can exhibit much more more, can expect a richer physics. So thanks very much.
Thank you. So thank you very much. I think it was a wonderful talk, very clear. So we have maybe some questions, maybe from the panelists. Burkhard, you have a first question maybe, and then.
Yeah, thank you for this very, very interesting talk. It's really great results which you have achieved. If you allow, I have a comment and I have a question. The comment is we have seen similar effects, but not with electrons, but with magnons, and you achieve that simply for YIG, which is of course a wonderful insulator. If you have obliquely, if you have a magnetization which is obliquely in oblique direction, yeah, so it's not perpendicular, but in some oblique direction, because then the non-reciprocity simply generates you some standing wave patterns which are actually moving and which act like a Taulas pump. Yeah, we haven't used your terminology. We have used a different terminology, but I was just realizing while you were presenting your talk that it could be very, very similar. And I would just like to ask you what is going on there. My key question to you is: you have talked a lot about dynamic magnetization. You have not used the word magnons, and you have not used the word coherency. So, I mean, normally, if you have spin waves, if you have dynamics with finite wave vector components, which you always have, if you have a finite size object, and so on, all these effects become very important. You get interference and so on. How would that modify, or would even be new physics come in, or would your field match to the field we are studying in Kaiserslautern? That is my question to you.
Oh, thanks for this really great question, I think. So I think even for the traditional current-induced work, then we have this issue, right? Whether the system reacts uniformly or it can excite, finite K spin wave. I think, almost all the questions that have been previously studied based on current-induced work become a new issue with our proposed voltage-induced work. So yes, I do acknowledge that this is a very crucial question. So I think the way we're going to study this is to run a micromagnetic simulation. So here we have the analytical, we have a semi-analytical theory for the voltage-induced work. Then we're going to use the, put this into the micromagnetics and see what happens if there's indeed a finite K spin wave modes can be excited by this voltage-induced work.
I'm very curious about your results, which will come up.
Oh yeah, thanks very much. Yeah, I'm also looking forward to what happens when this goes to micromagnetics. But I think even when spin wave modes are excited, the mechanical efficiency is still expected to be extremely high. So I think, the specific, pattern of the electrical response may be very different if there's a spin wave, but the mechanical efficiency is, it's very high, I think. And thanks for the question.
But mine spin waves are currents of angular momentum.
Yes, yes, spin waves do carry angular momentum. So here, because we consider, so in our scenario, the torque turns out to be the field-like torque. So in order to excite spin wave, which carry finite angular momentum, I think probably we need a damping-like torque. But in this topological insulator heater structure, we didn't find any, well, we do have a very small damping-like component, but we don't think that it's, can dominate the effect. But when generalizing the idea, to two-dimensional intrinsic magnetic TIs, probably we could find some damping-like components in the voltage-induced torque. If that happens, then probably it's able to excite the spin wave modes. I'm not sure if I have answered your question.
We would need to discuss. We would really put because the way you describe it in your terminology is very different from that what we used, coming of course from the spin wave community.
Yeah.
But we should do it maybe separately, not here.
Maybe I have a question. So within your mechanism here, the voltage-induced one, I was wondering, you may have it already, I think, within your calculations, but I didn't quite see it directly. So the heat generation, the entropy, in this case, because it's a charge current that you're generating, whereas the pumping one is intrinsically dissipationless. Where's the heat, once you generate those, where's the heat going to? How is that being dissipated?
You mean the energy? Would you repeat the last part of your question?
The energy dissipation, where is that going from or to?
Okay.
How is it coupling? Because essentially the pumping itself will be adiabatic, and then it would be definitely not loss of any energy, but how is that being generated? Because it being an insulator, you temperately, if you're pumping energy, your energy will go somewhere. The heat, essentially, the entropy generation of heat will essentially increase your temperature infinitely. Essentially, it's not far, it will be into nonlinear effects. But it was not clear to me how that's conceived.
So here, the energy flow is the following. So the input electric power converted into the magnetization dynamics, and then it dissipates into waste heat through Gilbert damping. So here, basically, the Gilbert damping is the only dissipative channel. Well, the direct Ohm's loss by the currents is eliminated.
Okay.
But I mean, because our goal is to drive the magnetization dynamics efficiently. So, compensating the Gilbert damping is actually regarded as useful work. This is not a waste work.
But will that heat, eventually will go to the phononic system, and then eventually, this is assuming that the Gilbert damping assumes that it goes into the phononic system in one direction, right? And it heats it up. How much of a heating do you expect from this type of effects?
How much heating?
Yeah.
Let's see, that also depends
Which is an insulator in this case, yeah.
That also depends on many factors. For example, the susceptibility. The larger the dynamical susceptibility, then the more dissipative power through Gilbert damping we would obtain. And that also depends.
No, but I'm saying, given that power that you calculate from the Gilbert damping, that actually does have a damping of angular momentum, but it does go somewhere. It goes essentially effectively to heat up the system.
Of course,
phonons, eventually, because they're making that assumption. But it is still an assumption because you still have a spin-orbit coupling involved and other things. Yeah, in a perfect system, you wouldn't have that damping. How much of the heating would you then have in your cycles?
Right.
Would that raise your temperature effectively compared to the typical? Because in insulators, things can, they usually would they just heat in the heat will be dissipated completely in the metallic leads, or how would it work?
Right. So let's see. Okay. So here, I think the way to estimate that. Okay. So here, this is we have a peak value on resonance for the overall admittance. And then let's say I also have a fixed voltage from the battery. Then the voltage is squared times this peak value of the admittance. That it's a very rough estimate of the dissipative power. Yeah,
then you have to integrate through a cycle, but then that's the question essentially. How much are you going up, and then will it reach a steady state? Will it not, or will it just hit it too much?
Yeah, I honestly don't have a good number off the top of my head, but I gonna estimate this and
very good for the experimental case. I think it will be a useful number to have.
Right, that is a good question. So yeah, so we indeed need this number. But by intuition, I would expect that the dissipation rate is lower than a current-driven system in which the heating effect arises from both the Gilbert damping and the Ohm's loss.
Yeah, they will make
Right.
law. Yeah.
Yeah, it might be weaker than that.
Yeah, but it's a closed system, so it could also be that it's you up.
Yeah.
Because the other one dissipates at the edges.
Yeah, let me just take note. This is a really good point.
I think experimentally it would be good to have that for the experimentalists, particularly because at the end of the day, it's an insulator, but it always has to couple somewhere to a metal to measure things and stuff. So
yeah, thanks for the
not so
question.
clear,
Okay. So now I have two things to do on my work on my to-do list.
Sorry about that.
The spin wave generation and the heating power, and compared with the traditional current-induced dynamics.
I think that would be a good. Also, it will motivate some of the people that are using other devices, maybe if it's a favorable. So do we have any further questions for the ideas? I think today is Eastern or something. I think maybe people are on vacation. Unfortunately, hopefully people watch the talk later. Most of the times we have about 70 people in the audience today, compared to the usual a little larger numbers. But I think it's Eastern that is gotten in the way. It's nothing to do with you getting up early, because here it's not early. Do we have any further questions from anybody in the audience for now? If not, I would like to thank, I'm going to stop the streaming now. Let me stop it here. And thank you once again